Okay, so linear approximations it's a really cool idea, very practical too, but kind of just the basic idea is as follows. Ooh. And so this is kind of a simple implementation of linear approximations, but you can extend this further on into approximating other crazy kind of functions. So, but let's just say, suppose you want to approximate let's say, how about 16, oh, not 16, sorry, 16.3 to the 3 halves, something like that. I don't know. So obviously you can do this with a calculator, right? But the idea is, let's use a little bit of calculus to approximate this value. So let's take a look at the function here. Okay, so if I replace 16.3 with x, then this approximation that I'm looking at would be the same as taking a look at the function x to the 3 halves, right? And let's see, let me erase this a little there. Okay, x to the 3 halves, and then plugging in 16.3, right? So it's the same, just a different way of writing it. Okay, so what does x to the 3 halves look like? Any ideas? The graph, yeah. What does the graph of x to the 3 halves look like? Is that one of the graphs that we know off the top of our head? No? Okay. That's okay. Well, yeah, I don't know. Good question. Let's graph it. Let's ask Desmos what it looks like. It goes up and down, right? All right, x to the 3 halves. Up. It only goes up. Okay. All right, so okay, so it looks kind of like that. Okay, well that's fine. So if I just kind of graph it here, something like that ish, sort of. Okay, and let's just say that whoa, what just happened? Oh, somehow that's strange. Okay, let's say here's 16.3, right, which is the value I'm trying to approximate, and this is f of 16.3. All right, can you guys see that? Okay. Okay. All right, so this is the one that I want to find out. You guys agree with that? Okay, so for the purposes of this, just pretend like we don't have a calculator. Calculators don't exist. We're back 2 centuries in the past, and we've lost all our calculators. Why? Well, because we can easily just plug it in, right? Now, just keep in mind, well, why would you care about this if you now have calculators? This is used in a lot of different applications, not with simple functions like this one. This is just to illustrate the idea. Does that make sense? Okay. All right. So this is the idea. Is for example, if I ask you, okay, what's the closest x value that you could easily evaluate that function at? The closest one to this point. 16, right? So 16 would be a pretty easy one. So if I, for example, right here, so let's just say, I'm going to make it, I'm going to say 16 is right here. Okay, so this one I know that f of 16 is equal to 16 to the 3 halves. What is that? Yeah, it's 64, right? So it's square root of 16 cubed, right? So that would be 64? Yeah? Okay. All right, so the y value here is 64. Okay, so the basic idea, it's not very complicated. All it is you take a point that's close to the one you're looking for, right? So in this case, 16. Find the tangent line there. So if I, Ed, do I know how to find the tangent line at 16? Would I be able to? If I, yeah? Okay, good. All right, so if I find the tangent line and I draw it right here, it would look like that. Okay, so this is the tangent line of f of x at x equals to 16. And I'm going to call it L of x. Okay, so what does L stand for? No? Maybe line? Okay, well no, it actually stands for the linearization of f of x at x equals to 16. Okay, so tangent line of the function, linearization of the function. What's the difference? Starts with N and ends with G. Nothing, that's right. Same thing, just different way of saying the same thing. Yes, Cal, you had a question?
Oh, never mind.
You were wondering what that was. It's a fancy sounding word. Yes, okay. So nothing, same thing. Tangent line, linearization of the function. Okay, now, here's the key thing to notice. If I zoom in even closer, oh, look at that. Okay, let me pick a different color here. How about blue? Okay. Right here, this is the one that I want, right? This was 16 to the, oh, sorry, not 16. That was 16 point, what was it, 3? Yeah. So 3 halves, right? That's the one that I was looking for. Okay, now, what do you notice about that right there on the point on the line compared to the point that I'm looking for? They're very close, right? So this is close to L at 16.3, right? So in other words, this point right here, the point on the line, is an approximation to the one that we are looking for because it's close. Do you guys agree? Yes? No? Yeah. Okay, so it's a linear approximation. You're approximating a value with a line. Okay, all right. Now, so let's zoom back a bit here. Okay, so what would be the benefit? Well, why don't we find it so that we can take a look here. So what is the wowzers? Okay, all right. Why don't we find the tangent line? Tangent line. All right, what do we do to find the tangent line? Okay, so what's the derivative? Okay, so 3 halves x to the 1 half, or 3 halves square root of x, right? Okay, so then what's the slope of the tangent line? It's the derivative at, careful, we'll look at the tangent line. Where am I finding the tangent line? At 16 or 16.3? At 16, right? Okay, so at 16, so this is 3 halves times the square root of 16, right? And what is that?
6.
That's 6, right? Okay, so the slope of the tangent line is 6, and then what's the, let's see, what else are we missing? Let me see, can I write it over here? So the slope is, yeah, we need the equation. So the slope is 6, and then we need a point. What's a point on the line?
The x value.
So what's the x value? Where am I finding the tangent line? 16, yep. What's the y value? 64, right? Notice how all those are easy to find, right? Because I found the tangent line at 16, which is easy to find, right? And so all easy numbers. Okay, so then the tangent line, or the linearization, is equal to, what would that be? 6 times x minus 16, right? Plus what? You guys are looking at it like you've never done it before. So you have the slope of a line and you have a point on the line. How do you write down the equation of the line? Y equals mx plus b, or the point slope form, right? Which is, this is how we've been doing it, no? Isn't it plus 64? Yes? No?
Doing y equals mx plus b. Plugging in, solving for b.
Yeah, we could do that too, sure. You guys want to do that instead? Okay, what's the y-intercept? So y equals mx plus b, right? We can do that. So y is 64, right? Slope is 6, x is 16, plus b. So what does b end up being? Six times 16 is? Okay, so b is negative 32. All right, so then the tangent line is, let's see here. Oh, I'll write it down over here again. Okay, so the tangent line is 6x minus 32. Okay, so that's the equation of the tangent line that we drew here in red, yes? Okay, so then what do? We're trying to figure out what this point right here is, the one that's close to it, right? That's our approximation. So then what are we going to do if we're looking for that point right there? Plug in the hard point into, so 16.3 into, not the function this time, I plug it into the tangent line, right? So, okay, so then this is going to be equal to 6 times x, which is 16.3, right? Minus 32. And then what is that? Well, what does that look like? 6 times 16.3, that would be 97.8, okay. Minus 32, which is 60, not 61, 65.8, right? Yes or no? Yeah. Okay, so what are we saying? So we're saying that let's see. Oh, this right here, 16.3 to the 3/2 is approximately equal to 65.8. Okay, so how close do you guys think we are?
Very close.
Pretty close. Okay. So what's the actual? Let's see. Somebody has a calculator and can do this for us. What would that be? How much?
65.808.
65. Why is this not doing it? I don't know. Okay. 65 point what? 808. That's pretty good, right? For a linear approximation. So what helps me that that makes it a good approximation? If you look at it, you can. It's really close, right? So for example, if I wanted to, okay, so let's just say, let's do a thought experiment here. Let's say you wanted to use the same, just for fun, same approximation to estimate, let's say, oh, I don't know, 25 to the 3/2. So we're not going to make a new line. We're going to use the exact same one just to approximate it at a different point. So what would we do? We would say, okay, well, let's plug in 25, right? So what would that be? That would be 6 times 25 minus 32. What is that? 118, yep. Okay, but then what's the actual? If I do 25 raised to the 3/2, it's 125. So is that a good approximation? That's not a good approximation. You're off by 7. That's bad, right? So why is it bad? Well, if you look at it, so here's the line, right? The red line. Where am I approximating it? If I tried to graph this, so this would keep going, right? Like that. And if I graph the line and I keep graphing it, notice how the farther I go from the point where I started approximating, the worse the approximation gets, right? See how far off I am now? Does that make sense? Yes.
And so with this, you would have to always try to find a new tangent length close to the value you're trying to approximate.
Right, exactly. Yeah. So if I wanted to approximate close to 25, well, 25 is actually easy to calculate, right? But yeah, you want to try to get as close as possible to the point you're trying to approximate. Yes.
Is there a definition of what close is, or is it just kind of that's good?
Well, it depends on how accurate you want to be. Yeah. So yeah, I mean, it really just depends. So yeah, I mean, for us mainly it's more about getting the idea. So in Calculus 2, you learn about extending the idea of approximating from linear to quadratic, cubic, and then so you extend the polynomials to higher and higher degrees to get more functions that approximate it better. So the higher the degree you go, the better the approximation will be. Kind of the idea is, for example, let me see here. Here, let me show you another. Let's see. Let me do this one, I guess. Okay. For example, let's say you have. So here, let me just to show you a little. So you'll learn more about this in the next calculus class. But let's say you take sine of x, right? Now, if you, let's say you're going to approximate near 0, right? So if I draw the tangent line at 0, it looks kind of like that, right? So if you look at it, the approximation is pretty good close to 0, but it gets pretty bad once you go a little bit farther away, right? Okay, but for example, if I draw a cubic function, so if you think of a cubic, how many humps can it have? Up to 2, right? So if I draw a cubic, so for example, maybe I could have a cubic that kind of goes like, oh my gosh, what's happening here? Kind of goes like this, like, I feel feel like I'm running out of ink. What's happening? Okay, I don't know what's happening, but okay. All right. So what do you think about the cubic? Yeah, it approximates it for a longer interval, right? Well, but sine, keeps having more and more, it has infinitely many humps, right? So if you want to approximate it for a longer interval, what do you need to do? You need to keep raising the degree of the polynomial so that you can have more humps, right? So this is a cubic, and then if you wanted, if you go up to, say, 5th degree, maybe you would get something that looks like, oh wait, let me do, I don't know. So, something like this, and then it has to go like that, let's say. So what's that? 1, 2, 3, 4 humps. 2, 3, 4. 1, 2, 3, 4. Okay, something like that. Does that make sense? Sort of? So that's the idea anyways. But you'll learn more about that in chapter 2. Yes?
I was going to say, like with sine, or like with any sort of trig function, since they're periodic, and even though they're infinite, if you found your tangent approximation within one period, could you apply that to any infinite, like, period? Say you wanted to find, like, like 32 pi over some crazy number, but you found, whatever that tangent approximation was within the first period from origin, could you apply it?
You can by, just doing a shift. Sure. Yeah. Okay. All right. So let's do another one. Let's say let's see here. All right. So let's do another example. So let's say you want to approximate. How about sine of I don't know. Sine of 0.75, let's say. By finding the linearization of sine of x at what would be a good point? Not pi over 2. So think of pi as about 3, right? So you want it to be close to 0.75, so pi over 4, right? Because if pi is about 3, and then, so 3 divided by 4 is 0.75, so pi over 4 sounds pretty good, right? Okay, so does that make sense? Yeah? All right, so basically what are we doing? If we kind of just think about what we're actually doing, what's the only thing we need to do? Find the linearization, okay, which is the same thing as saying you find the derivative, but to find the derivative so you can find the tangent line, exactly. So that's all you're doing. You're finding the tangent line of the function. The main thing is don't get confused with the two different points that you have. So that's the biggest mistake students do is, so we're going to find the tangent line here at pi over 4. And then after that, we're going to plug in a number into the tangent line. What's that number? What's the number that I plug into the tangent line? 0.75, exactly. Does that make sense? So that's the basic idea here. Okay, so let's do it then. So the derivative, right? You guys said. So what is it? Cosine x, good. So then the slope is f prime at pi over 4, right? So what's cosine of pi over 4? Okay, root 2 over 2. So then I have y equals mx plus b, right? So what's my y value?
That's 1.
Plug it into the original function, right? So this is sine of pi over 4, right? So pi over 4 is where I'm finding the tangent line, right? Okay, what is sine of pi over 4? Okay, root 2 over 2. And then what about... Okay, and then the slope we said is root 2 over 2. What's the x value? Pi over 4. Okay, and then we solve for b, right? So then we have root 2 over 2 equals to root 2 over 2 times pi over 4 plus b. So b is equal to root 2 over 2 times 1 minus pi over 4. Okay. So this is b. So is that enough to find the equation of the tangent line?
Yes.
Sure it is, right? Okay. So let's see here. So, okay. So then we have L of x is equal to, so what would I have?
Root 2 over 2x plus
Root 2 over 2x plus, and then what I just found for b, right? So 1 minus pi over 4. Something like that. Okay, so that's called again, the linearization, right? Linearization of sine of x at pi over 4, right? Okay, and then what's the approximation? So the approximation would be so let's see. So we would have sine of 0.75 is approximately equal to. So how do I approximate it? What's the next step? Plug in 0.75 into the tangent line, right? So L at 0.75, which is root 2 over 2 times 0.75 plus root 2 over 2 times 1 minus pi over 4. And whatever that is, I don't know what that is. Somebody have a calculator? What would that be? Square root of 2 divided by 2 plus times 1 minus pi over 4. Okay. So my calculator says 0.85.
You forgot to multiply it by
Oh!
5. Yeah.
What is it? Oh, you're right. Okay. Just want to make sure you guys are paying attention.
Thank you.
Times 0.75. Okay. All right. So my calculator says 0.6821. Okay. So how good of an approximation is that? So what's the actual? 0.68 what?
164.
164. Okay. So pretty close, right? Yeah, that's pretty good. Any other questions with that? No? Does that make sense? Yeah. You guys want to try one? What do you guys think? You guys want to try one? All right, so let's see. So what's the function that you guys decided on? Square root of x. One thing to note is that it doesn't necessarily have to be square root of x. It could be, for example, square root of x plus, I don't know, 64, for example. Well, what number would you plug in there to get square root of 65? 1, right? So, not that you should do that. I'm just saying that you can. So, square root of x is kind of the natural choice because it's a little bit easier to work with. But if you're, say, for example, given a different function, you should be able to still just plug in a different number and make it work. So, like, well, yeah, so I'll just leave it at that. Okay, so then what did you guys do? You got the derivative, right? Which was 1 over 2 root x, right? Okay, so that gave you the slope, which is the derivative at... Yeah, I forgot to mention. So 64 is the point that we're going to evaluate the, find the tangent line at, right? Because we know what the square root of 64 is. Does that make sense? Okay, so let's see here. So this is 1 over 2 square root of 64, which is 1/16. Okay, so that's the slope. Let's see, what else? So then find the y-intercept, right? So y equals mx plus b. So then, let's see, what's y? 8? So where does the y value come from? Yeah, you plug in the x value into the original function, right? So square root of 64, which is 8. Does that make sense? Yeah? Okay. And then what did we say the slope is? Slope is 1/16. What is x? 64. Good. And then, okay, so then what did you find for b? 4. 4? Okay, all right. So then we have, let's see. So L, the linearization is equal to 1/16 x plus 4. Notice that so far, how many times have I used 65 or square root of 65? We have not used it at all, right? So one of the most common mistakes that I see here is students start plugging in that number into random places, you know, so like maybe they'll plug in 65 here, or sometimes even square root of 65, and so then the numbers kind of get jumbled up. So you just have to be careful, make sure that you understand the idea. Remember, we're finding the tangent line not at the point that we're given, we're finding it at a different one because it's easier to find it there. Does that make sense? And only when we find the tangent line do we then say, okay, well, we can now approximate the question, right, which was square root of 65. This is approximately equal to evaluating the tangent line where? At 65. Notice not at the square root of 65. You're evaluating the tangent line at 65. Is it clear why we're doing that? Or is there a question why that is? Or no? You guys are okay? Okay, all right. So this is 1/16 times 65 plus 4. And what is that? 8.0625. Okay, and then what's the actual? 0.06226. So the error is pretty small, right? So just subtract the actual minus the 226. Okay. And whatever that is, what is that? 0.00. I'm losing the 0.3. Wait, 5? No, not 3. 1. Right? Can't tell what that number is anymore. That's a 5, that's a 6. Okay. That's pretty good, right? Okay, so questions with that. Does that make sense? Easy peasy lemon squeezy? Yeah? Any doubts, confusions? No? Everything's good? Okay.